Welcome to this walkthrough of LeetCode problem number 1341, titled No Data Available. While details about the problem are missing, we'll explore potential approaches, discuss complexities, and extract valuable insights to enhance your problem-solving skills. Let's get started. LeetCode problem number 1341, titled No Data Available, currently lacks any published information. This could mean the problem has not yet been released or is unavailable for other reasons. Without details such as a problem statement, examples, or constraints, it is not possible to provide a walkthrough or create related content. If you are looking for help with a specific algorithm or problem-solving strategy, please provide more context or specify another problem. When approaching a problem like LeetCode number 1341, where no data is available, it's essential to rely on structured problem-solving techniques. The first step is to understand the context. In competitive programming or real-world scenarios, when details are missing, clarifying the requirements becomes critical. On a platform like LeetCode, this could involve investigating why details are unavailable, such as checking if the problem is unpublished or under development. In an interview setting, asking the right clarifying questions ensures you don't waste time solving the wrong problem. Additionally, identifying categories and patterns is a helpful strategy. Even with minimal information, we can infer potential problem types based on the title or problem number. Knowing that LeetCode often categorizes problems into areas like arrays, graphs, or dynamic programming enables us to brainstorm possible directions for a solution. Once you've assessed the context, the next step involves considering generalized approaches. Starting with brute force is a common initial strategy. While inefficient, it provides a baseline solution and helps uncover patterns in the problem. For instance, brute force might involve testing all combinations or possibilities, which, though computationally expensive, can reveal opportunities for optimization. From there, we refine the approach using more advanced techniques like sliding windows, binary search, or dynamic programming. These methods allow for efficient solutions tailored to the problem's structure. It's also important to evaluate trade-offs. Without clear constraints, you must balance time complexity, space complexity, and implementation complexity. For example, a highly optimized algorithm may reduce runtime but could require significant memory or intricate coding. Making informed assumptions about the problem's scope helps guide these decisions. In the absence of a specific problem statement for number 1341, the chosen strategy would focus on iterative development and assumption testing. The first step is to clarify requirements by seeking additional information. This might involve checking related problems, the problem title, or consulting with a problem setter or stakeholder. When no further details are available, forming reasonable assumptions becomes key. Testing these assumptions through small examples or edge cases can help validate your approach. From there, we begin with a brute force solution to gain insights into the problem structure. By observing patterns during testing, we can incrementally optimize the solution. This iterative cycle of development, testing, and refinement ensures that even with limited information, progress can still be made. In a real-world setting, this approach is especially useful for navigating ambiguity while maintaining a logical framework. The core insight here is that problem-solving is fundamentally an iterative process. Even when faced with incomplete information, a structured approach helps you navigate uncertainty. Recognizing common problem-solving patterns, such as divide-and-conquer or greedy algorithms, allows you to draw on prior knowledge and apply it to new scenarios. This ability to generalize is particularly powerful when details are sparse. However, it's equally important to weigh the trade-offs between different approaches. For example, brute force solutions are straightforward to implement but often computationally expensive, making them ideal for initial exploration. Optimized approaches, while more efficient, require a deeper understanding of the problem's structure and can be harder to develop without concrete details. Ultimately, these strategies, clarifying requirements, testing assumptions, and iterating on solutions, are universally applicable and underscore the importance of a methodical mindset in problem solving, even when details are missing. When tackling any algorithmic problem, the first step is to thoroughly understand the problem requirements. Begin by clarifying the inputs, outputs, and constraints. Ask yourself questions like, what type of data is provided? Is it an array, string, or perhaps a graph? What should the output look like?
Is it a single integer, a Boolean value, or maybe a list of elements?
Additionally, consider any constraints or edge cases, like whether the input could be empty, contain negative numbers, or be very large. For instance, if you're tasked with finding the maximum sum in an array, you'd want to confirm if the array can include zeros, negative numbers, or duplicates. These details guide your understanding and help avoid misinterpretation of the problem requirements, ensuring a strong foundation for building a solution.
Once you have a clear understanding of the problem, the next step is to explore example cases.
This helps you build intuition and identify potential edge cases early on. Start with simple examples to make sure you understand the basic mechanics, and then gradually increase the complexity of your test cases. For instance, if the problem involves arrays, try testing with an empty array, a single element array, and arrays with repetitive or extreme values. After that, think about how to approach the problem. Choosing the right strategy is crucial because the efficiency of your solution often depends on it.
For smaller inputs, brute force may be sufficient, but for more complex problems, techniques like divide and conquer, dynamic programming, or greedy algorithms might be more appropriate.
For graph-related problems, breadth-first or depth-first search can be effective, while array and string problems often benefit from sorting or two-pointer techniques. The key is to align the problem's constraints with the most suitable algorithmic approach, especially for large inputs, where you'll want to avoid inefficient solutions like O(n)².
After selecting an approach, it's time to implement the solution. Write clean, modular code by breaking your logic into functions to enhance readability and maintainability.
Be sure to comment on critical sections of your code to explain the purpose of specific operations.
Once implemented, move on to testing. This step is vital to ensure correctness and robustness.
Test your solution with edge cases, such as empty inputs or invalid data, and verify its performance with large datasets.
Neglecting these tests could lead to issues in real-world applications.
Remember, the constraints of the data often dictate the feasibility of your approach.
For example, if you're working with very large inputs, your solution must prioritize efficiency.
Finally, pay close attention to edge cases, they're critical for avoiding unexpected failures. Testing with scenarios like null inputs, empty lists, or unusual patterns in the data can reveal weaknesses in your solution that need addressing.
Optimization is an essential part of refining your solution.
Initially, you might start with a brute force method to get a working baseline, but it's important to analyze its bottlenecks and look for opportunities to improve. For example, if you're using nested loops, consider replacing them with a hash map to reduce lookup times and enhance performance. The choice of data structures can also play a significant role in optimization. Arrays and lists are great for sequential data, often working well with two-pointer techniques to optimize searches or comparisons. Hash maps and hash sets are ideal for quick lookups and avoiding duplicate computations, while stacks and queues are commonly used in graph traversal problems like depth-first and breadth-first searches.
Graphs themselves can be represented with adjacency lists or matrices, depending on the problem's requirements.
Lastly, heaps are powerful for priority-based operations, such as finding the kth largest element. By carefully selecting and leveraging the right data structures, you can significantly improve the efficiency of your solution. To solidify these concepts, let's walk through an example problem, finding two numbers in an array that add up to a target sum. The simplest approach is brute force, checking all pairs of numbers to find one that matches the target. While straightforward, this method has a time complexity of O(n)², which can be inefficient for large inputs.
Instead, an optimized approach uses a hash map.
As you iterate through the array, calculate the complement needed to reach the target and check if it already exists in the hash map. If it does, you found your pair; if not, add the current number's complement to the map. This method reduces the time complexity to O(n). Don't forget to account for edge cases, such as an empty array, a single element array, or scenarios where no pairs meet the target. By combining a clear understanding of the problem, an efficient algorithm, and robust edge case handling, you can arrive at an optimal solution. Since the exact details of LeetCode problem number 1341 are unavailable, this Python implementation provides a general framework for solving algorithmic problems. The solve method is defined within the solution class, which is the typical structure for LeetCode problems. Inside the solve method, we assume the input data is passed as a parameter named input_data. The code includes placeholder logic to process the input data, such as iterating through it and performing an example operation, in this case, summing the values.
The result is then returned.
Once the problem details are known, you can replace the placeholder logic with the actual algorithm to solve the problem.
Edge cases and specific constraints should also be handled accordingly based on the problem's requirements. This is the Java implementation of the placeholder logic for LeetCode problem number 1341. The code mirrors the Python implementation, using Java-specific syntax and conventions.
Key differences include type declarations for arrays, the enhanced for loop for iteration, and the use of Java collections where needed. The solve method processes an integer array, adding all elements to compute the result.
A main method is included to demonstrate the functionality with example input. We begin our solution walkthrough with the first example, where the input data is 1, 2, 3, 4. Initially, we set our variable result to 0. Next, we start iterating through the input data. The first item in the list is 1.
Adding this to the current value of result, which is 0, we get a new result value of 1. Moving on to the second item, which is 2, we add it to the current result value, 1, resulting in a new value of 3.
Then, we process the third item, 3. Adding this to the current result value, 3, updates result to 6. Now, we process the final item in the input data, which is 4.
Adding this to the current result value, 6, gives us a final result of 10.
For this example, the output is 10.
Moving on to the second example, the input data is 5, 10, 15. Again, we initialize result to 0.
Starting the iteration, the first item is 5. Adding it to the current result, 0, updates the result to 5.
Next, the second item, 10, is added to the current result value, 5, which results in a new result of 15. For the third item in the input data, which is 15, adding it to the current result value, 15, gives us a final result of 30. So, the output for this example is 30. Now, for the third example, the input data is 0, 0, 0, 0.
As before, we initialize result to 0. Starting the iteration, the first item is 0.
Adding this to the current result, 0, keeps the result unchanged at 0. The next item is also 0, and adding it to the current result, 0, still leaves result at 0.
The third item in the input data is 0.
Adding this to the current result, 0, again leaves the result unchanged at 0.
Finally, we process the last item, which is also 0.
Adding it to the current result, 0, results in a final result of 0.
For this example, the output is 0.
This demonstrates how the solution handles cases with all zeros, correctly maintaining the sum as 0 throughout.
Here, we begin by analyzing the time complexity of the solution.
The algorithm processes the input data by iterating through it once, performing a simple addition operation for each element. If we denote the size of the input data as n, we can break the time complexity into 3 parts. First, parsing the input is assumed to have no additional preprocessing, which takes constant time, or O1. Next, the loop iterates through all n elements, and since each iteration only involves a constant time operation, this step contributes O(n) to the time complexity. Finally, the return statement at the end also runs in constant time, O1. When we combine these components, the overall time complexity simplifies to O1 plus O(n) plus O1, which is O(n). This linear time complexity ensures that the algorithm scales efficiently as the size of the input grows. Now, let's examine the space complexity of the solution. The algorithm operates directly on the input data without making a copy, meaning the storage for input data is external to the algorithm and does not add any extra memory overhead. The only auxiliary variable used is the integer result, which is updated during the iteration. Since this variable requires a constant amount of memory, it contributes O1 to the space complexity. Additionally, no other data structures are created, so the overall memory usage remains the same regardless of the size of the input. Combining these factors, the total space complexity of the solution is O1, making it highly space efficient. We can better understand the efficiency of the current approach by comparing it to a brute force or naive method. A brute force solution might involve unnecessary operations, such as creating new data structures to store intermediate results or iterating through the data multiple times. For example, summing numbers using a naive approach might involve nested loops or generating a new array of cumulative sums, which could result in n squared, time complexity and potentially higher space usage. In contrast, the current approach achieves an optimal n time complexity by processing the input in a single pass and 1 space complexity by avoiding additional memory allocation. Importantly, this algorithm's performance holds steady across best, average, and worst cases, as it always performs a single iteration through the input data. This consistency ensures both time and space complexities remain n and 1, respectively. Finally, let's solidify our understanding with a mathematical proof for the time and space complexities. The core of the algorithm is the for loop, which iterates n times, where each iteration performs a constant time addition operation. This makes the total time spent in the loop directly proportional to n. Since no other part of the algorithm contributes a factor that depends on n, the overall time complexity is n. Meanwhile, the memory usage of the algorithm is determined by the single auxiliary variable result, which does not scale with the size of the input. Therefore, the space complexity is 1. In conclusion, the algorithm achieves optimal performance, being both time efficient and space efficient, with complexities of n and 1, respectively. One of the most common mistakes when solving coding problems is not fully understanding the problem statement. It's easy to rush into coding without taking the time to clarify edge cases or constraints, but this often leads to solutions that fail under specific conditions. To address this, always spend time analyzing the inputs, outputs, and edge cases before writing a single line of code. Another frequent pitfall is ignoring edge cases. For example, scenarios like empty arrays, single elements, or maximum constraints can easily be overlooked. While your solution might work for standard cases, failing to account for these corner cases can result in test case failures. The best practice here is to explicitly test these edge cases after you complete your initial implementation. Lastly, using inefficient algorithms is a major issue. Brute force methods might work for small test cases, but they often fail to meet time constraints for larger inputs. To avoid this, analyze the time and space complexity of your approach and consider optimized patterns such as two-pointers, binary search, or dynamic programming when appropriate. Another mistake to watch out for is overcomplicating the solution. It's tempting to add extra data structures or over-engineer the algorithm, but this can make your code harder to debug and less efficient. Instead, aim for simplicity and clarity by adhering to the keep it simple principle. Overcomplication often leads to unnecessary confusion, so always prioritize straightforward solutions that get the job done. Additionally, not validating input constraints is a critical error. Assuming all inputs strictly adhere to constraints without validation can result in runtime errors or incorrect outputs. To prevent this, include checks for invalid inputs in your implementation and handle them gracefully. By addressing these two issues, overcomplication and lack of input validation, you'll create solutions that are both robust and efficient. When tackling coding problems, especially in interviews, there are a few key insights to keep in mind. First, pattern recognition is crucial. Many problems revolve around common patterns like sliding windows, divide and conquer, or dynamic programming. The faster you can identify the underlying pattern, the more efficiently you can approach the problem. Optimization thinking is another important skill. Once you arrive at an initial solution, always ask yourself if there's a way to improve it. For instance, reducing an n squared solution to n can make a huge difference in performance. Clear communication is also vital. Interviewers appreciate candidates who explain their approach step by step, including any trade-offs, before diving into coding. Additionally, dry running your code with sample inputs can help catch logical bugs early, saving time during debugging. Lastly, manage your time wisely. Allocate the first 5 to 10 minutes to planning, about 20 to 25 minutes to coding, and reserve the remaining time for debugging and optimization. This structured approach ensures you make the most of your interview time. To strengthen your understanding of the problem at hand, it's helpful to explore related problems. For instance, LeetCode number 121, best time to buy and sell stock, focuses on finding the maximum profit with a single transaction.
It's a great example of how to optimize solutions within given constraints. Another related problem is LeetCode number 53, maximum subarray, which uses Cadon's algorithm to solve subarray problems efficiently. Similarly, LeetCode number 152, maximum product subarray, involves dynamically handling both positive and negative values, offering insights into how to manage complex scenarios. Finally, LeetCode number 42, trapping rainwater, is a classic optimization problem that tests your ability to apply techniques like two-pointers or dynamic programming. Exploring these problems can provide valuable practice with patterns and strategies that are often applicable to other challenges. When solving problems, it's important to understand the trade-offs between different approaches. Brute force methods are simple to implement and can be useful for small test cases or when exploring the problem space. However, they become inefficient as the input size grows. For scenarios where performance is critical, optimized approaches like dynamic programming or sliding windows are a better choice. These require a deeper understanding and careful implementation, but they significantly improve performance for large inputs. In cases where the data is sorted or the problem can be broken into subproblems, techniques like binary search or divide and conquer are often the most efficient. While these methods may require additional pre-processing or a recursive mindset, their efficiency makes them ideal for handling structured data or recursive problem scenarios. By choosing the right approach for a given context, you can balance simplicity, performance, and implementation effort effectively. Thank you for joining this walkthrough. While the problem details were unavailable, we discussed how to approach ambiguous challenges, emphasizing adaptability and systematic thinking. If you found this helpful, consider subscribing for more coding insights. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!